Okay, so it's almost 3 p.m. It's 3 minutes to 3 p.m. So I'll just wait for 5 more minutes and to check if anyone joins. So this is the week 12 3 session for constraint and unconstrained optimization codes. So this is will be the last TA session, and yeah, after that there is an exam I think next week. So I'll just post uh, 1 hour video summarizing everything that you have learned in the course after I post this week's TA session. So probably that will come out sometime tonight or tomorrow. Okay, so I'll wait and I'll get started with the content once someone joins or after a few minutes. Okay, so it's 3 p.m. already, so I'll get started with today's content. So the topic of discussion will be just the week 12 assignment solution because all the course content is over, right? So, and it will be a very short discussion because uh, I don't think it will take a lot of time to solve this assignment, probably half an hour or so. So after that, I'll just wait uh, if there is anyone who joins or if anyone asks any doubts. Otherwise, I'll summarize everything and we'll close the session at 5. So, so let me start with week 12 assignment solution. So that's the main agenda of this week's article session. So as per always, I'll write down the question and also I'll do the solution. Okay, so so the topics that were covered was the barrier and penalty method. So mostly the interior penalty method, the barrier method was covered in this week's content. And also then there was a discussion on dynamic programming and multi-objective optimization or multi-attribute optimization. Those things were also discussed. Okay, so the first question is a theoretical question related to the interior barrier function method. So I'll write down the problem. So it says interior barrier function method generates a sequence of solutions xk by minimizing the function qx comma ck. This is equals, so I'll write it down in the next line. Qx comma ck equals f of x minus ck times bx. Then which of the following is not true for the variable function, which is bx? Which of the following are true for the variable function bx? Okay, so write down the options. I hope my internet is fine so far. Option A is bx tending to 0 as x approaches to the optimal solution. Next is bx tending to 1 as x approaches the optimal solution. Option C is bx tending to minus infinity as x approaches to the optimal solution. So if you remember, this variable function is typically a log function or say a reciprocal function 1 by something. And that is kind of converging to say 0, then the reciprocal at the variable function should converge to infinity. And that is the option that is given in option D. So this is kind of self-explanatory and I think was discussed in the class. But yeah, that's the logic that you can use. And this is absolutely true that Vx will tend to infinity as x approaches to the optimal solution. All right, so the answer I'll write down for this. The answer is option D, and yeah, it is the correct. So this was kind of easy, self-explanatory. So let me move on to the second problem. So again, it's very similar. So since I have time, I'll just wait for to see if anyone joins, and then I'll get started. Let me start with the second problem. So it's also on interior penalty function method, and now it's on the coefficient or the penalty parameter that you have. Okay, so it says interior penalty function method generates a sequence of solutions x by minimizing the function. Again, it's the same function, the scale function, so which of the following now is true. For the penalty parameter, which is CK, right? Okay, so I'll write down the options. First is CKR. So it depends on the sign plus whether it's monotonically increasing or decreasing. So CKR non-negative and monotonically increasing. CKR negative and monotonically increasing. So actually, the penalty parameter is not negative. So this option automatically is not true. Then CK, so A could be a potential answer. Let's see the third option. CK are non-negative and monotonically decreasing. So actually, this is true in interior penalty method. You start with a high value of CK and you kind of decrease it and can bring it to zero, or it tends to zero. And then D is CKR negative, which is again not true. Option A is also not true, by the way, uh, and monotonically decreasing. Okay, so only one option is correct, which is option C. Again, this is self-explanatory. So if you have gone through the lecture, it's pretty straightforward. I think everyone will has answered this correctly. Okay, so we have one person joining in. Okay, so I was solving the week 12 assignment problem. So yeah, I've just mentioned the answers for the first two questions. I'll solve the third one right now. If you have any doubt, you can go ahead and ask. So yeah, the third problem, I'll write it down. So you have to minimize f x1 comma x2 equals 2x1 square plus 9x2, and this is subjected to x1 plus x2 greater than equals 4, and you have x1 and x2 are non-negative. So you have to solve this optimization problem using the interior variable function method. So solve the above optimization problem uh, by using interior variable function method. Okay, so the options are A is x1 star x2 star equals 2 comma 2. This is the second one, 2.25, 1.75. C is the this one is 1 and 1.75. And option D is 2.25 and 2, I think. Yeah. Okay, so let me solve this problem. So for this, okay, I'll just write down the problem once more. So it's min of fx1 is 2 x1 squared plus 9x2 subjected to x1 plus x2 greater than equals 4. So actually you can convert it as a less than equals to type constraint, because we need to deal with gx less than equals to 0 type constraint. So I can take this minus 4 to the other side as well. Yeah, so this will be your constraint, and x1 and x2 are greater than equals 0. So you can construct your q function first, and this is nothing but f of x minus ck times that b of x, then you can use 1 by gx here. So the function here is 2x1 squared plus 9x2. And this is minus ck, and minus 1 by x plus x1 plus x2 minus 4. So you can write it as 2x1 squared plus 9x2 plus ck divided by x1 plus x2 minus 4. You can take the gradient of this function. So let me take that. The first term is 4x1. And for the second term, what you have is minus k plus x1 plus x2 minus 4 whole square, and yeah, x1, so that will be 1 itself. Next one is 9, and it will be a similar term. Yeah, in fact, exactly the same term that we have here. Okay, so now what you can do, you can set this to 0, 0 by first order necessity conditions, and that that will give you ck by x1 plus x2 minus 4 whole square equals 4x1, And from the second one, it gives you equals 9. So that means x1 is 2.25, which is 9 by 4. And for the so what you can do, you have to get the value of x2 from here. So for that, what you can do, let's use the second equation. So it gives you ck by 2.25 plus x2 minus 4 whole square equals 9. Then this is ck divided by x2 minus 1.75 whole square equals 9. Or you get it as x2 minus 1.75 whole square equals ck by 9. Now, for this method, what you have to do, as ck tends to 0, uh, your solution moves towards the optimality. So for that, what happens is that x2 minus 1.75 whole square is also tending to 0. So that means x2 is 1.75 at optimality. So actually it should be a small x2. Yeah. So x1 is 2.25 and x2 is 1.75. This is your answer. So I think option B is the correct one. Yeah. Yeah. So option B is the correct answer here. See. Okay, so B is correct. So let me now move on to the fourth problem. So I think it's again a similar type of problem. You have to solve an optimization problem using the interior barrier function method. Okay, so the fourth problem tells you minimize fx1 x2 1/3 of x1 plus 1 whole cube plus x2. This is subject to. Okay, so we have x1 greater than equals 1 and x2 greater than equals 0. Solve the optimization problem by using interior barrier function method. Okay, so the options are, option A is x1 square x2 square equals 1 comma 0. Option B is 0 comma 0. Option C is 1 comma 1. And option D is 0 comma 1. Okay, so now let me solve this problem. So for this, again, what I can do, I can write down the initial statement, which is v of fx1 x2 equals 1/3. Okay, so this is your objective function, and your constraints are x1 greater than equals 1, so you have to convert it as minus x1 less than equals minus 1, or minus x1 plus 1 less than equals 0, and your other constraint is x2 greater than equals 0. So you can keep this one as it is, but we are treating it as gx type of constraint. So you can also put minus x2 less than equals 0. So this is equivalent to your g1x. This is equivalent to your g2x. And now your q values, you can write it as, so this is minus ck, and this can be this g1x, and this can be plus g2x. Okay, so this one is 1/3 x1 plus 1 whole cube plus x2. This is minus ck. This is 1 by 1 minus x1 plus 1 by minus of x2. So you can write it as, by taking a minus common, this can be plus ck by x1 minus 1 plus 1 by x2. Okay, this you can write it like this. Now you have to take the gradient of this function. So when you take the gradient, the first term is 1/3 times 3 x1 plus 1 whole square, and there won't be anything for the second term. The third term will give you plus ck, or okay, plus ck 1 by x1 minus 1 whole square. Actually it should be a minus, so times minus 1. Yeah, the rest is fine. And from the second term you will get, for x2 is, it is 1, and then it's plus ck by x2 square, and again a minus 1 multiplied it. Okay, so let me simplify it. So this is x1 plus 1 whole square, and then this is minus ck divided by x1 minus 1 whole square, and this is 1 minus ck by x2 square. As before, you can also set this one to 0, 0. Okay, so in that case, what you will get is, the second term gives you, or let me deal with both the terms together. The first one gives you this. So if you multiply them, so that's x1 square minus 1 whole square equals ck. Okay, and the second term gives you 1 equals ck by x2 square, or x2 square equals ck. Now what you have is, as ck tends to 0, so x2 square tending to 0, that means x2 is 0, and x1 square minus 1 whole square is tending to 0. That means x1 square equals 1, and that means x1 is 1 because it is given that x1 is greater than equals 1, so it cannot take a value of -1. So the answer here would be x1 star x2 star is 1 comma 0. So let's see which one was the correct one. Yeah, option A is correct, I think. Yeah, that was also there in that. Yeah, so option A is correct. This was straightforward. Okay, so now let me move to the fifth problem. So I think fifth and sixth are kind of similar again. They are connected to each other. And in one, I think you have to find the optimal solution, like the x values, and in the other, you have to get the function value. Yeah. So let me write down the problem. So this is a fifth problem where you have to maximize fx1, comma x2, comma x3, comma x4 equals x1, x2, x3, x4, and this is subjected to x1 plus x2 plus x3 plus x4 equals 100. Now the problem asks you the optimal solution of the above optimization problem. Is, so option A is x1 star, comma x2 star, x3 star, x4 star. So this is 97, 1, 1, 1. Option B is this is equals 25, 25, 20, and 30. Option C is all of this are 25, and option D 5, 15, 35, and 45. Okay, so let me solve this problem. So let me write down this. Okay, this is equals to x1, x2, x3, x4. So this has the flavor of the dynamic programming thing that you have learned in this week's content. Let me do that. So what you have to do, you have to first define certain variables. Was there a, okay, so there were no non-negativity constraint in the problem. But anyway, since you are multiplying it, okay, let me check. Okay, let me try and solve this first and then check if that non-negativity thing is required or not. Okay, so what you can do, you can write x1, oh sorry, s1 as x1, then you can write s2 as x1 plus x2, then you can write s3 as x1 plus x2 plus x3, and S4 as x1 plus x2 plus x3 plus x4. So that means your S4 is 100, your S3 is nothing but your S4 minus x4, which is 100 minus x4. This is nothing but S3 minus x3. So your S3 is 100 minus x4, and this is minus x3. And this is S2 minus x2. Your this is your, yeah. So once you know x4, uh, you can know s3, and then you have to know x3s and sorry, I think this I have written it wrong. It should be x2. Yeah. So I think since s4 is known, so it's you have to kind of backtrack and get the value of x4 first, and then the others you can find it out easily. Okay, so you can write it in terms of first, let's do in this forward direction. So f1 s1 equals x1, that you can consider, and x1 you can consider it to be s2 minus x2, and f2 s2. Now you can think of it as a variable in terms of variable x2. So this is maximization of, with respect to x2, and then you are multiplying x2 times f1 s1. So that's equivalent to just considering the first two terms. So that's max of x2. This is x2, and f1 s1 is nothing but s2 minus x2. Now this is just an unconstrained problem, and you can take the first derivative, and the first order condition will give you s2 minus 2x2, and you can set this to 0, and your x2 star becomes s2 by 2. Now what you can do, you can set this value. So your x2 is known, so that means your f2 x2, sorry, f2 s2 is so that's uh, x2 times x1. So this is s2 by 2 times s2 minus of s2 by 2. So this becomes s2 squared by 4. Now let's deal with considering the third term. So now you can maximize with respect to x3, and you have the rest of the term, which is so x3 I can write it down, and then it's f2 s2, and you can write it in terms of x3, and this is s2 squared by 4. And also you can s2 you can replace it by okay, let me keep it this way, or okay, I think I can replace it in terms of s3 minus x3. Yeah. This is s3 minus x3 whole square divided by 4. Now let me multiply everything, or let me keep it this way and just get the derivative. So it's df3s3 by dx3. So this is x3 times 2 s3 minus x3, and divided by 4. there should be a -1 plus x3 minus x3 whole square divided by 4. So this gives me, I can take 4 as common, and this is becoming minus 2x3. Okay, so I can further simplify this. S3 squared plus S3 squared is 2 S3 S3 minus 2 x3 S3 plus 2 x3 squared divided by 4. Or let me not do it this way. I can simplify it in another way. Yeah, instead of expanding, let me take this as common. This becomes minus 2x3. Okay. Now you can set this to 0. Now there are two possibilities. If S3 is equals to x3, then the thing that becomes is that x1 plus x2 becomes 0. But that means x1 and x2 will individually becoming 0. So that should not be the case. That's why from here, the only possibility should be s3 minus 3x3 equals 0. Or you can write it as x3 star equals s3 by 3. And then you can also write your f3 of s3 equals, so that's x3 minus, multiplied by this whole square by 4. So you can put it as s3 by 3. This is as s3 by 12. And then you have 2s3 by 3 also. So this gives you s3 by 12 and then 4 s3 squared by 9. So this gives you s3 cubed by 27. Okay, hope I have done this correctly. Then the final one that is remaining is f4 of s4. So for that you can do max of x4 times f3 of s3. As before, what you can do, you can put that value, so s3 cubed by 27, and s3 is nothing but s4 minus x4. Okay, so from here again I have to differentiate it with respect to x4. So in that case, the first term remains as it is. Then we have 3s4 minus x4 is 27 minus 1 plus, okay, so as before, I'll simplify it. Minus 3x4. Okay, let me take this as common. This is divided by 27. This is 4x4 by 27. So as before, I can set this as 0. The first term won't be 0 because that makes the other terms as 0 and your multiplication will become 0. So that's not the case. So this one will be true. Or you can write it as x4 star equals s4 by 4. And you know the value of s4, which is 100. So this is nothing but 25. So once you know that, let's plug the other things back in. So once you know x4, you can get, x3 star. So x3 star is s4 minus x4 star, which is 100 minus 20. Uh, Sorry, I think I made a mistake. This should be s3. Okay, so this is 75. But I think, yeah, this is 75. So this is your s3. And x3 star is s3 by 3. So x3 star is s3 by 3, which is 75 by 3, which is 25. So once you know this, you also know s2, which is s3 minus x3 star. So that's 75 minus 25, which is 50. So once you know s2, uh, you can know x2 star, which is s2 by 2. So x2 star is 2 by 2, which is 50 by 2 and 25. So that gives you your S1 as S2 minus x2 star, which is 50 minus 25 equals 25, which is also your x1 star. So that means the solution that you are getting is all 25. So let me check which one was the correct answer. Yeah, option C is correct here. C is correct. Now, I think the sixth problem tells you to find the objective function value of this problem. So it will be 25 to the power 4. So I think, so anyway, I'll just for the sake of completeness, I'll write it down and tell you which one is the correct answer. Okay, the sixth problem is the optimal objective value of the optimization problem is f x1 star x2 star 3 star 4 star. Okay, so this is what you want, and let me write down the options. A is 10 to the power 4, B is 25 to the power 4, C is 25 times 25 times 20 times 30, and option D is 5 times 15 times 35 times 45. Okay, clearly, so option B is the correct answer here. So there's B. That's all about the sixth problem. So I have four more problems to discuss, and I think two of them are just theoretical ones, but anyway, I'll write it down and solve it. The seventh problem tells you which of the following is or are true about multi-objective decision making. So, which of the following is or are true about multi-objective decision or MODM, you can call it. So the options are MODM problems always have a unique always unique optimal solution. Well, this is not actually true when you have conflicting objectives. So this won't be the correct answer. B is saying that MODM problems have a set of non-dominated or Pareto optimal solutions. So actually, this will be true. And I think this was discussed in the lecture 59 or 60. Option C is, in general, the objectives in MODM are in conflicting nature with each other. So this is also true. Each other. Option D is none of this. So for this one, option B and C will be the correct one, and this is kind of self-explanatory, so I'm not going into the details of it. So, yeah, I think everyone has got this correct anyway. So the eighth problem, it's similar and it's on multi-attribute decision making. So it tells you, so I'll write down the problem. So eighth is, which of the following is or are true about multi-attribute decision making? Multi-attribute decision making, or call it as MADM. So the options are MADM problems always have a unique optimal solution, which is also not true, just like before. Option B is medium problems always have infinite number of finite number of, so this is not true actually. number of non-dominated solutions, because in multi-attribute case, when you have finite number of attributes, so this might not be the case. Okay. Option C is MIDM problems have a set of non-dominated or Pareto-optimal solutions, which is true. And I think this was explained in the 60th lecture of the course. So I think this is self-explanatory, so I need not explain further. And D is none of this. Yeah. So option C is the correct one here. So I'll just write it down. So answer is C. Okay, so now let me move on to the ninth and 10th problem. So those are the only two problems remaining in this assignment. So the ninth problem, so these are a bit of a numerical thing, but it's not that difficult actually. It's straightforward, and I think it was discussed in the classes. So you have this minimization of f1x and f2x. So you have two objective functions or two terms in the objective function, whatever you call it. So this is the first one and this is the second one. And you have x greater than equal 0. So solve the above multi-objective optimization problem to find Pareto-optimal solutions. Okay, so the options are A is x belongs to 0, 2, so these are closed intervals. X belongs to -1, 2. C is X belongs to 2, 10. And D is none of this. Okay, so let me see how we can solve this problem. Okay, so for this problem, actually, I think in the class there it was discussed, and also the graph of these two functions were also drawn. But yeah, I'm not drawing the graphs here as such, but let me do it mathematically. So you have f1x equals root x plus 1 and x greater than equals 0. So that means uh, what you have here is that since x is greater than equals to 0, so this function has a minimum, and it is an increasing function that you can notice. So f1x has its minimum at x equals 0. Then what you have is that f2x is x squared minus 4x plus 5. So you can take the derivative and set it to 0 and x equals to 2. The second derivative is positive, which is 2. So that means f2x has its minimum at x equals to 2. Now you can notice that I have mentioned, yeah, so f1x is an increasing function for x greater than equals 0, and f2 prime x is 2x minus 4. So that means if x is greater than equals 0, then it's an increasing function. But if x is greater than less than equals to 2, sorry, so let me write down this actually. So f2x is an increasing function for x greater than equals 2. But f2x is, an, is a decreasing function for x less than equals to 2. So it has minimum at x equals to 2, and since it's a decreasing function, so the values are kind of higher than that in between 0 and 2. And the same goes for the other function, which is f1x. So the values are kind of higher than what it has at x equals to 0. And also you can find out the values at x equals to 0 and x equals to 2 for these functions. So the main thing to notice is that, so let me also write down this f1 0 equals 1, f1 2 is root 3, f2 0 is 5, f2 2 is 2 square, which is 5. Okay, so this will be 1. But in between, the functions are having a conflicting nature, right? So one is kind of increasing, and the other is also a decreasing function in between 0 and 1, right? So let me write down the objectives f1 x and f2x are conflicting in nature between 0 and 2, that is x belongs to 0, 2. So, so this implies that 0, 2 is the Pareto optimal interval or Pareto optimal solutions, right? Pareto optimal interval, you can call it. So this is the correct answer, and option A is correct here in this case. So this was again directly from the class, but it requires some maths to you can do it, or you can also draw the graphs of these two functions, and you can notice in which portion it is increasing and which portion it is decreasing, right? Okay, so that's all about the ninth one. So I'm now only left with the 10th problem, and after that I'll just probably that will be the discussion for this week, and you can ask your doubts after that if you have any. Otherwise, yeah, I'll call it a day. Okay, so solve the following multi-attribute optimization problem to find out Pareto solution of flight choice. Okay, so the data that you are given is, so this is flight, this is fare, so that's your one criteria or one attribute, and the other attribute is time. So this is flight A, for which you have a fare of 15,000 and the time required is 3 hours. B is uh, the same fare, and this is 2 hours 30 minutes. Flight C is 12,000, 4 hours, and flight D is 15,500, and this is 3 hours. Okay, so let me write down the options for the Pareto solution. So first one says flight A and C are Pareto solutions. Option B is flight A and D are Pareto solutions. Okay. Option C is flight C and D are Pareto solutions. And option D is flight B and C are Pareto solutions. Okay, now let me solve this problem. So what you have here is that two attributes, which is fare and time, and you will try to minimize both of them. And but it might happen that for some flight the fare is higher, but the time is lesser. And so the objectives are kind of conflicting with each other. So that's why you have to go for the Pareto solutions. So the way you can solve it is, so let's check the first column, which is the fare column, and check for flights which are having same price. So flight A and B are having same fare, right? So fare of flight A equals fare of flight B. But what you have is that the time by for flight B, so or you can write, but time of flight A is greater than time of flight B. So that means flight B dominates. So flight B dominates flight, or it is more preferable than flight A. So obviously A won't be in the Pareto solution. So option A and option B are you need not consider that. And clearly you can see that only option D contains this B. So D should be the correct one, but let's check for flight C as well. So now you know that A is eliminated. Now you can also check for, you can compare D and A, right? Because they have the same time. So you can write it as uh, time of flight D equals time of flight A. But fare of flight D is higher than. So fare of flight D is greater than fare of flight A. So that means flight A dominates flight T, and it automatically means that flight B dominates flight T. Okay, so now flight C, the cost is cheaper than all the other flights, but the time is highest compared to all the other flights. So it's not dominated by any of the other flights because these are kind of conflicting in nature. So you can write that flight C is not dominated. The reason being is that it has the cheapest fare by any of the flights, any of the other flights. So that means both B and C are Pareto solutions. So therefore, flight B and C are Pareto solutions. Okay, so option D is the correct one. So this was also straightforward. Okay, so that's all about this week 12 assignment solutions. So yeah, since that's all about the content of this week, so I'll stop for today. So I'll just hang around for a bit. If there is any question, you can ask. Otherwise, you can leave the meeting. And I'll wait till like 5 p.m. is the scheduled time so that if anyone has any doubt, they can ask those. Hi, Kasturi. So actually, I was discussing the week 12 assignment problem. So I'm done discussing that. So if you have any doubts, you can ask. Otherwise, like you can leave the meeting if you want. Okay, since it's 5 p.m. already and no one else has joined, and I have solved all the problems in week 12 assignment. So that's all from this course, and best of luck with your exams next week. So what I'll try to do, I'll just post probably one more video of 1 hour or so, summarizing everything that you got learned in this course. Okay, so thank you all. And yeah, the discussion forum questions, I think the latest one I cannot answer those because those are mostly related to specifically the assignments and also the videos that the instructors posted. So hope the mentee of the course or the course instructor replies those messages. Okay, so with that, yeah, I'll stop for today and yeah, so I'll post the other video. Thank you.